In this video, I will be discussing about integration of hyperbolic functions. The study of integral calculus would not be complete if we will not make a reasonable amount of discussion in the integration of hyperbolic functions. In fact, these functions occur frequently in applied mathematics, more especially on science and engineering. Now, we've already learned from your previous calculus that by definition, a hyperbolic function is a combination of exponential functions. So that is why, by definition, the hyperbolic sine of u is equal to e to the power u minus e to the negative u divided by 2. And the hyperbolic cosine of u is equal to e to the power u plus e to the negative u all over 2. Now, that is the basic definition of hyperbolic functions. Now, we have here 8 additional formulas in our list of integration formulas. So we have the integral of hyperbolic sine of u du, which is equal to the hyperbolic cosine of u plus c. And the integral of the hyperbolic cosine of u du is equal to the hyperbolic sine of u plus c. And then, formula 28 is the integral of the hyperbolic tangent of u du, which is equal to the natural log of the hyperbolic cosine of u plus the constant of integration c. Also, for the integral of the hyperbolic cotangent of u du is equal to the natural log of the absolute value of the hyperbolic sine of u plus the constant of integration c. And then we have here the integral of the hyperbolic secant squared of u du, which is equal to the hyperbolic tangent of u plus c. And also the integral of the hyperbolic cosecant squared of u du, which is equal to the negative hyperbolic cotangent of u plus c. And we have the last two formulas for the integral of the hyperbolic secant of u times the hyperbolic tangent of u du, which is equal to the negative hyperbolic secant of u plus c. And the integral of the hyperbolic cosecant of u times the hyperbolic cotangent of u du, which is equal to the negative of the hyperbolic cosecant of u plus c. So we will use this formula in integrating hyperbolic functions. For example, number 1, what is the integral of the hyperbolic sine of x over 2 dx? Now in this case, this integrand resembles the integrand in our first formula, wherein our u there is this x over 2. Now, if we let u be equal to x over 2, our du is equal to 1/2 dx here. And then, because we don't have 1/2 in our integrand, we need to eliminate the 2 in this denominator by multiplying both sides of the equation by 2. So we have 2 du, which is equal to dx here. Now, by substitution, we have the integral of the hyperbolic sine of u, because x over 2 is our u here, and then our dx is 2 du. So instead of writing dx, you will write 2 du. And then factoring the constant of 2 outside the integral symbol, we have 2 times the integral of the hyperbolic sine of u du here. Thus, this form resembles our first formula there. So, therefore, our integral is the hyperbolic cosine of u plus the constant of integration c. And then substituting back our representation of u, which is x over 2, we have 2 times the hyperbolic cosine of x over 2 plus the constant of integration c. So this is now our answer for this example number 1. So number 2, what is the integral of the hyperbolic secant of the square root of x times the hyperbolic tangent of the square root of x all over square root of x dx? Now, looking at this integrand, we notice that it is somewhat like in integral formula 32, because if you let your u be equal to this square root of x, we notice that our du here, which is the derivative of the square root of x, is 1 over 2 square root of x dx. And because we don't have a 2 in our integrand here, we need to eliminate this 2 by multiplying both sides of the equation by 2. So this is 2 du, which is equal to dx over the square root of x. So therefore, we can rewrite this integrand as the hyperbolic secant of the square root of x times the hyperbolic tangent of the square root of x, and this square root of x will be the denominator of our dx here. So by substitution, we have the integral of the hyperbolic secant of u, because our u is the square root of x, and then multiplied by the hyperbolic tangent of u, and then times this dx over the square root of x, which is our 2 du there. So this is multiplied by 2 du. So factoring the constant outside the integral symbol, we have the 2 times the integral of the hyperbolic secant of u times the hyperbolic tangent of u du. Now, looking at this integrand resembles our formula 32. So therefore, we can apply the formula as the negative of the hyperbolic secant of u plus the constant of integration c. Now, substituting back our variable, we have negative 2 times the hyperbolic secant of u, which is the square root of x, plus the constant of integration c. So therefore, this is our answer when we integrate this integrand here. And at this point, let us proceed to our example number 3. What is the integral of x cubed times the hyperbolic cotangent of x to the power of 4 dx? Now, looking at this integrand, it might resembles a formula 29 here, but we have an extra x cubed there. So at a first guess, we say that our u is the x to the power of 4, and our guess will be a correct guess, because if we take the differential of this x to the power of 4, this is 4x cubed dx. But we don't have a number 4 in our integrand, so we need to divide both sides of the equation by 4. So this is du over 4, which is equal to x cubed dx. And this gives the idea to rewrite our integrand here as the integral of the hyperbolic cotangent of x to the power of 4 times x cubed dx here. And by substitution, we have the integral of the hyperbolic cotangent of u, because x to the power of 4 is our u now, but our x cubed dx is our du over 4. So instead of writing x cubed dx, we will write its equivalent representation, which is du over 4 here. And factoring the constant outside of the integral, we have 1/4 times the integral of the hyperbolic cotangent of u du there. So at this time, we can apply the formula number 29, that is equal to the natural log of the absolute value of the hyperbolic sine of u plus the constant of integration c. And then going back to the original variable, our u is equal to x to the power of 4. So this is 1/4 times the natural log of the absolute value of the hyperbolic sine of x to the power of 4 plus the constant of integration c. And this is our answer for this integration number 3. Now, let's proceed to our fourth example here. What is the integral of the hyperbolic secant squared of 2x plus 3 dx? Now, looking at this integrand, we suspect that we can apply formula 30 here by representing our u as 2x plus 3. Because if you take the differential of u, this is 2 dx here, because the derivative of 2x is 2 and the derivative of 3 is 0. And since we don't have a number 2 as a coefficient of this function, we need to eliminate the 2 by dividing both sides of the equation by 2. So what will remain on the right side is dx. So by substitution, we have the integral of the hyperbolic secant squared of u, because our 2x plus 3 is our u now, but our dx is our du over 2. So instead of writing dx, you will write du over 2. So factoring 2 in the denominator outside the integral symbol, we have 1/2 times the integral of the hyperbolic secant squared of u du. And applying formula number 30 here, that is equal to 1/2 of the hyperbolic tangent of u plus the constant of integration c. So going back to our original variable u, which is equal to 2x plus 3, our answer is 1/2 of the hyperbolic tangent of 2x plus 3. And this is added to our constant of integration c. So therefore, this is our answer for this example number 4 here. So moving to our last example, we have the integral of e to the power 2x times the hyperbolic cosine of 2x dx. We noticed that our integrand is composed of a product of two different functions, the exponential function and the hyperbolic function, hyperbolic cosine of 2x. But we know that hyperbolic functions are defined in terms of exponential functions. So it is logical to express the product in terms of the same functions. So since our first function is e to the 2x, we don't disturb our first function. But our hyperbolic cosine of 2x can be converted to its equivalent exponential functions using its definition that this is equal to this. So using this definition, this is equal to e to the power 2x plus e to the power negative 2x all over 2 here. So factoring the constant of 1/2 outside the integral symbol, we have the integral of e to the 2x times e to the 2x plus e to the negative 2x dx. And distributing our factor here to this binomial, we have 1/2 of the integral of e to the power 2x plus 2x, because when multiplying expressions of the same base, we just add the exponent. So this is also added to e to the power of 2x plus the negative 2x. And of course, there is a dx here. So this is equal to 1/2 of the integral of e to the power 4x plus e to the power 0, because 2x plus the negative 2x is 0. And then applying the integral of a sum rule, we have 1/2 of the integral of e to the power 4x dx plus 1/2 of the integral of e to the power 0 dx. And if we let our exponent be equal to u, which is 4x, we notice that differential of 4x is 4 dx. But we don't have a 4 in this integrand here, so we need to eliminate 4 by dividing both sides of the equation by 4. So therefore, by substitution, we have 1/2 of the integral of e to the power of u, because our 4x is our u this time, and our dx is du over 4. So instead of writing dx, you will write du over 4. And this is added to 1/2 of the integral of 1 dx, because e to the power 0 is 1. So factoring the constant of 1/4 outside the integral symbol, we have 1/2 times 1/4 times the integral of e to the power u du plus 1/2 of the integral of dx. And we know that the integral of e to the power u is e to the power u. And this is added to 1/2 of the integral of dx, which is x. And this is added to the constant of integration c. So going back to our original variable, which is 4x, we have 1/8 e to the power 4x plus 1/2 of x plus the constant of integration c. And this is our answer for this example number 5. So to continue in this video, we will add 6 more formulas here, and these are integrations that would lead to the inverse hyperbolic functions. So formula 34, we have the integral of du over the square root of u squared plus a squared is equal to the inverse hyperbolic sine of u over a plus the constant of integration c. Or you can have the natural log of u plus the square root of u squared plus a squared plus c, because we know from your previous calculus that the inverse hyperbolic functions are logarithmic functions, which is in the same way that hyperbolic functions are exponential functions, because inverse hyperbolic functions and hyperbolic functions are inverses to one another. Therefore, we expect logarithmic functions are inverse hyperbolic functions. So formula 35, we have the integral of du over the square root of u squared minus a squared is equal to the inverse hyperbolic cosine of u over a plus c, or that is the natural log of u plus the square root of u squared minus a squared plus the constant of integration c. And we have the next two, which are almost the same, because in the denominator here is a squared minus u squared, but here it's u squared minus a squared. And their answers are all inverse hyperbolic functions, which are also logarithmic functions. And we have also the last two, which are almost the same, because here in the denominator we have a squared minus u squared inside the square root symbol, but here inside the square root symbol we have a squared plus u squared. And their answers are also inverse hyperbolic functions, which are actually logarithmic functions. So to apply this formula here, let's have our first example. What is the integral of dx over the square root of 4x squared minus 9? Now, looking at these 6 formulas, we suspect that it might be formula 35. Why? Because 4x squared is a square term inside the square root symbol. And we have also 9, which is also a perfect square, which resembles a squared. So if we will write this one as the integral of dx over the square root of 2x quantity squared, if you express this 4x squared as a square value, and this 9 also as 3 squared, so it's a difference of 2 squares, then we say that our u here is equal to 2x. And if we get the differential of our u, this is 2 dx. But we don't have the 2 in our integrand there as a coefficient. We need to eliminate 2 by dividing both sides of the equation by 2. So we have du over 2, which is equal to dx. So by substitution, we have the integral of dx, which is du over 2. So instead of writing dx, you will write du over 2. And this is over the square root of u squared, because 2x is our u here, but we need to square, and then we know that our a also is 3. So this is a squared also. Then factoring the constant of 1/2 here. So we have 1/2 of the integral of du over the square root of u squared minus a squared. And you notice that this is the same as formula 35. So we can apply the formula and say that this is equal to the inverse hyperbolic cosine of our u over a. And this will be added to our constant of integration c. So going back to our original variable, we have the inverse hyperbolic cosine of u over a, but our u is 2x and our a is 3 here. And this is added to the constant of integration c. So our answer is 1/2 times the inverse hyperbolic cosine of 2x over 3 plus the constant of integration c. Or you may write its equivalent function, which is 1/2 of the natural log of your u, which is 2x plus the square root of your u squared minus a. But your u is 2x, so u squared 2x, we have 4x squared. And then we subtract the square of your a, which is 9. So this is also added to our constant of integration c. And this is our answer for this example number 1. So let's proceed to our example number 2. We have the integral of dx over x times the square root of 25 plus 4x squared. So we might suspect that this is a formula 39 because we have some x's outside the square root symbol. But as you can see, inside the radical symbol should be the sum of two squares. So we need to express this integrand where the radicand of our square root should be a sum of two squares. So this is 5 squared plus 2x quantity squared. So therefore our u in that expression is 2x. So if we get the derivative of our 2x, we have 2. So this is 2 dx. But we don't have a 2 in our dx here. So we need to eliminate 2 by dividing both sides of the equation by 2. So this is du over 2 is the value of our dx. And of course, our a is equal to 5 here. So by substitution, we have the integral of dx, but instead of writing dx, you will write its equivalent representation, which is du over 2. And then we have the denominator of x here. So to solve for x, we need to divide both sides of the equation here by 2. So we have u over 2 is our x. So instead of writing x, you will write its equivalent representation, which is u over 2. And then this is multiplied by the square root of a squared, because 5 is our a here, and our 2x is our u. So factoring the constants outside the integral symbol, we have 1/2 over 1/2. And this is multiplied to the integral of du over u, because we have a u here, and this is multiplied to the square root of a squared plus u squared. But we know that this 1/2 here and this 1/2 in the denominator cancels each other. So this is equal to 1 times the integral of this. And to integrate this one is to apply formula 39. And that is equal to the negative 1 over a times the inverse hyperbolic cosecant of the absolute value of u over a plus the constant of integration c. So going back to our original representations, original variable a, which is 5, we have negative 1/5 times the inverse hyperbolic cosecant of u over a, wherein u is 2x and our a is 5. And this is added to the constant of integration c. Or you may write its equivalent logarithmic form, which is equal to the negative 1/5 of the natural log of 5, because a is 5 here, and then this is added to the square root of your a squared, and your a is 5, so you square, that's 25, plus the u squared. And since our u is 2x, so when you square u, we have 4x squared. And this is over the absolute value of your u, which is 2x. And this is added to the constant of integration c. So this is our answer for our example number 2. So let's proceed to our example number 3 here, which is the integral of dx over the square root of x times the square root of 9 plus x. So how do you find the integral of that rational function? Now we see here that our radicand can be a sum of two squares when you let your u be equal to the square root of x. Since you can express that radicand as a sum of two squares, the square root of 3 squared plus the square of the square root of x, because the square of the square root of x is x. But when you take the differential of u, we have the differential of this, which is 1 over 2 square root of x dx. And because we don't have a 2 as a coefficient here in our integrand, we need to multiply both sides of the equation by 2. So we have 2 du, which is equal to dx over the square root of x. And this gives us the idea that this square root of x here is the denominator of dx. So we can rewrite this one as the integral of dx over the square root of x. And this is divided by the square root of 3 squared plus the square of the square root of x. And by substitution, this dx over the square root of x is our 2 du there. And the denominator, which is the square root of 3 squared, but 3 is our a here. So this becomes a squared plus the square root of x, which is our u now. So this is u squared. So factoring the constant there, we have 2 times the integral of du over the square root of the sum of a squared and u squared. And using our formula 34 there, we have 2 times the inverse hyperbolic sine of our u over a. And this is added to the constant of integration c. So substituting back our original variable, we have 2 times the inverse hyperbolic sine of u, which is the square root of x over a, which is 3 here. And this is added to the constant of integration c. Or you may write its answer to its equivalent logarithmic form, which is 2 times the natural log of the square root of x plus the square root of x plus 9, because the square of the square root of x is x and the square of 3 is 9. And this is added to the constant of integration c. So this is our answer for problem number 3. So let's proceed to our example number 4, which is the integral of dx over 6x minus x squared. Now you notice that there is an x squared term in the denominator, so therefore we can form a perfect square there. But since this x squared has a negative sign, it is logical to factor out the negative sign outside a parenthesis here. So this becomes positive, and positive 6x becomes negative inside the parenthesis with a negative sign. And then we can complete to form a perfect square trinomial here. So we have the integral of dx over negative of x squared minus 6x, and the third term is obtained by the square of the half of the numerical coefficient of the second term. So this is negative 6 divided by 2 is negative 3, and when you square, that's 9. And maybe you will ask, where did I get a 9 there? So to make a balance, I will add 9 here. Now, how can you obtain a balance? When you add 9, then you add 9 also. Actually, I'm not adding 9 here because it is preceded by a minus sign. So actually, I am subtracting 9 here. So to have a balance for the negative 9, I need to add 9 here. So as if I have done nothing to this expression, 6x minus x squared. So we can express this one as a difference of 2 squares this time. So this is 3 squared minus the square of x minus 3. So we notice that this is of the formula 36, wherein the denominator is a difference of 2 squares, wherein the first square is a square of a constant and the second square is a square of a polynomial. So in this case, our u there is x minus 3, because when we take the du, our derivative of this is just 1 dx, because the derivative of minus 3 is 0. And also our a is 3 here. And by substitution, we have the integral of du, because the representation of dx is du here. So instead of writing dx, you will write its representation, which is du over a squared, because 3 is a. So this is subtracted by u squared, because x minus 3 is our u here. So applying formula 36, this is equal to 1 over a times the inverse hyperbolic tangent of u over a plus the constant of integration c. So this is equal to 1 over a, but our a is 3, so this is 1/3 times the inverse hyperbolic tangent of u, but our u is x minus 3 over a, which is 3 here. And this is added to the constant of integration c. So this is our answer for example number 4. Now, let's proceed to our fifth example here, which is the integral of 5x plus 3. And this is divided by x squared plus 4x minus 5 dx here. So how do you integrate this integrand here? Now, at this point, our suspicion is to make a square in the denominator, but we know that this trinomial here is not a perfect square. So we form a square by grouping the terms. So this is 5x plus 3 over the denominator, which is x squared plus 4x, and we will make it as 1, then we subtract 5 here. And of course, there is a partner of the integral symbol, dx. So how will you make this 1 as a perfect square? To make that 1 as a perfect square, we need to add a third term. And what is that third term? That is equal to the square of the half of 4 here, which is 4. Because to get the third term for a perfect square trinomial, it's the square of the half of the coefficient of the second term. And the half of 4 is 2, and when you square 2, it's 4. But there is a minus 5 here. But because you are adding 4, I need a balance by subtracting 4. And of course, there is a partner of the integral, which is the dx. So at this time, we can form a square in the denominator this time. So this is 5x plus 3 times dx over the x plus 2 quantity squared minus 3 squared, because this trinomial here is a square of this binomial. And this 1 minus 5 and minus 4 is negative 9. However, if you let the denominator, which is this one here, the x plus 2 quantity squared minus 3 squared, we notice that if you get the differential of this u, this is 2 times x plus 2 dx, because the derivative of this one is this one here, and the derivative of minus 9 is 0. And removing this 2 here, we have du over 2, which is equal to x plus 2 quantity dx. So with this, we need to have this expression in the numerator of our integrand. So how do we form x plus 2 there? We can only form x plus 2 when we can factor out 5. So we have 5 times x plus 2. But to have that plus 2, when you factor out 5, we need a 10 there. So forming a 10 is to add a 10. So this is 5x plus 10 there. And where did I get a 10? I will also need a balance by subtracting 10. So this is divided by the denominator x plus 2 quantity squared minus 3 squared dx. Because if you factor a 5 in the numerator, we have 5 times x plus 2. And therefore, we come up with this one here. But we still have a minus 7 in the numerator. So this is divided by x plus 2 quantity squared minus 3 squared. There. So to solve this problem here is to divide these two terms of the numerator by this denominator here. So we have the integral of 5 times x plus 2 divided by x plus 2 quantity squared minus 3 squared dx. And then we separate our 7 here dx, but this is divided also still by x plus 2 quantity squared minus 3 squared. So factoring all the constants outside the integral symbol, we have 5 times the integral of x plus 2 times dx over the denominator, which is x plus 2 quantity squared minus 3 squared. And this will be subtracted by 7 when you factor out the 7 outside the integral symbol. So we have dx over the denominator x plus 2 quantity squared minus 3 squared. So this one can be solved if we apply formula 37 here, that this denominator is a difference of two squares, wherein the first square is a square of a polynomial and the second square is a square of a constant. So with this, we can represent v as x plus 2. So our dv here is dx and our a is 3. So by substitution, we have 5 times the integral of x plus 2 dx, which is this one here. So this is du over 2, and this is divided by this one, which is our u here. So this is u minus 7 times the integral of dv, because our dx here is our dv here, over this v squared, because x plus 2 here is our v. And this will be subtracted by a squared, because 3 is a. So factoring the constants outside, we have 5 halves times the integral of du over u minus 7 of the integral of dv over v squared minus a squared. So this is equal to 5 halves times the natural log of u minus 7 times 1 over 2a times the natural log of v plus a over v minus a here. And this is added to the constant of integration, c. So going back to our original variable, this is 5 halves times the natural log of u, but our u is this one. And if you simplify this one, this is equal to this denominator. So that is x squared plus 4x minus 5. And this is minus 7 over 6 because 2 times a, but our a is 3, so this is 2 times 3. And 2 times 3 is 6. And this is multiplied by the natural log of v. But our v is x plus 2. So x plus 2 plus a, that is x plus 5. And this is divided by x minus 1 because our v is x plus 2 and x plus 2 minus 3 is x minus 1. So this is our answer for this problem number 5. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.